Hello, everyone. Thanks for your interest. My name is Richard Ren, and I'm a PhD candidate at Carnegie Mellon University. Today, I'm going to present my work on multi-agent simultaneous multi-goal sequencing and pathfinding. So multi-agent pathfinding, or MAPF, is a problem about finding a set of collision-free paths for multiple agents from their respective start and goal locations. In this work, we consider a variant of MAPF where agents must collectively visit a large number of goals and stop at one of the destinations. Application of this problem can be found in logistics, surveillance, and so on and so forth. So now let's talk about the problem definition. So let's say we have a set of n agents represented by an index set. The environment shared by all agents is represented as a graph. In this problem, there is a set of m goal nodes in the graph that must be visited by at least one of the agents along its path, pi I. Additionally, every agent's path must end up with an arbitrary one of the destination. Totally, there are n destinations. So the planned joint path, pi, must also be conflict-free, which means for any pair of the agents, they cannot locate at the same node at the same time, or they cannot go through the same edge from the opposite direction at the same time. We also introduce a collision checking function, which takes a joint path as input and returns a subset of agents that collide along the joint path. In the graph, every edge has a non-negative cost value associated. The cost of a path is the sum of cost of all edges present in the path. The objective of this problem is to find a collision-free minimum cost joint path for all agents. So basically, this problem involves both multi-agent pathfinding and goal allocation and sequencing. We need to not only plan collision-free path for agents, but also compute an assignment of goals to agents and the visiting order of the assigned goals for each agent. To solve this problem, our approach brings together both subdimensional expansion, or M-star, for multi-agent pathfinding, and a transformation-based algorithm for multiple traveling salesman problem. We leverage M-star to plan paths for agents independently and couple them for planning only when collision happens. We leverage the transformation-based algorithm to generate a TSP problem from the original multiple TSP problem, and then compute the optimal tour. With this optimal tour, we can then extract the assignment as well as the optimal visiting order of goals for each agent. We name our algorithm MS-star, where M stands for multiple agents and S stands for Steiner TSP problem. So like other A-star-based heuristic search algorithms, MS-star systematically search over a state space for solution. Every search state in MS-star is defined as a tuple of a joint vertex V, which specifies the locations of all agents, and a binary vector of length m, which specifies the visiting status of each goal node. Note that at any time of the search, every state represents a partial solution joint path for all agents. To compare two states, we introduce two new types of dominance. So first, we introduce a dominance between binary vectors. I will skip reading the math here. Intuitively, it means that given two binary vectors, AK and AL, if AK dominates AL, it means every visited goal node in AL is also visited in AK. And AK has at least one goal node visited, one more goal node visited than AL. With that in hand, we can now introduce dominance between two states, SK and SL, that share the same joint vertex. So basically, it means that given two state SK and SL, we'll compare the set of goal nodes visited in both states, as well as the G values of the states. If one state SK outperforms the other state SL, then we say SK dominates SL, and SL can be pruned. Okay, next, let me introduce the goal sequencing procedure. So here, given a search state S, we can extract the current location of agents as well as the unvisited goal nodes of agents. So goal sequencing procedure here should compute a set of n goal sequences, which answers the question about how to assign those unvisited goals to agents and what's the visiting order for each agent. To achieve this, we use a transformation-based approach. This approach first generates a transformed graph where the edge costs are set in a well-designed manner. Then, in this transformed graph, an asymmetric traveling salesman problem solver is invoked, and an optimal tour within this transformed graph is computed. Finally, this optimal tour can be decomposed into a set of assigned goals with visiting orders specified for each agent. More details can be found in our paper. So far, we have covered state definition, dominance, and goal sequencing. Next, we're going to describe the pathfinding process, which is actually quite similar to M-star or say A-star search. The algorithm begins with the initial state, run goal sequencing for that state. And then with the computed goal sequences, a low-dimensional search space can be constructed, which is basically the shortest path for each agent to visit the visited goal, the assigned goals in order, ignoring any other agents, ignoring any potential collisions between agents. Then the algorithm will keep expanding states within this low-dimensional search space unless a collision between a subset of agents is detected. Then for this subset of agents in collision, the algorithm will expand the state by generating successor states while considering all possible moves of agents. Then for each newly generated successor states, goal sequencing is invoked to compute the goal sequences as that state. The algorithm terminates only when a goal state is expanded, which indicates that a collision-free join path with the minimum cost is found, and this path has visited all of the goals. And more details and analysis of the algorithm can be found in our paper. Okay, to test the proposed algorithm MS-star, we select several maps from an online benchmark set for MAPF. We change the number of goals and agents and then report the success rates under a time limit of 1 minute, as well as the average runtime of goal sequencing. So from the results, first of all, different maps have very different results. If we look at the curves with different colors in the plot, we can see that when the number of agents increases from 5 to 10 to 20, the success rate becomes lower and lower. On the other hand, the success rates are relatively stable with respect to the number of goals in the first 3 maps. Additionally, if we look at the average runtime of goal sequencing, it increases as we have more goals and more agents. Also, for the last map with 50 goals, the transformed graph in this case contains 20 starts, 20 destinations, and 50 goals, so totally 90 nodes. In this case, the algorithm times out in all instances, which indicates the limit of the current approach. We also simulate the result of the planner in a random 32 by 32 world with 20 agents. On the left, we have 20 goals to be visited, while on the right, we have 50 goals to be visited. Okay, to conclude, in this work, we introduce a problem called multi-agent simultaneous multi-goal sequencing and pathfinding. We propose an algorithm named MS-star to solve it and analyze its property. We also provide numerical results and simulation to verify the approach. For future work, one can consider modifying MS-star to solve variants of the problem. One can also consider fast approximation algorithms for goal sequencing to trade off between solution quality and computational efficiency. Okay, this is the end of my presentation, and thanks for watching.